Guys, welcome back to Stats with Warnke. This is part 2 of the 3.2 notes. So we're going to pick up where we left off last time with residuals. So in the last discussion that we had, we were looking at a residual, which was the actual amount minus the predicted amount. One of the things that we use that difference for is looking for patterns between our predictions and the estimate. A residual plot is what we can then make. So a residual plot is a scatter plot of the residuals against the explanatory variable. So that is our x. So we're just using whatever our x is in context, and then the y variable, or the y-axis, is our residual. So looking down here, whatever our x was in context, let's say it was miles driven, that's what we would write here, and then residual would be the label that goes along the y-axis. So Part A, or that little thing kind of subnote underneath residual plot, says if the residual plots are randomly dispersed on the horizontal axis and relatively small in size, a linear regression model is appropriate. Otherwise, a nonlinear model is more appropriate. So what we're looking for is random scatter. We're looking for no clear pattern. So here you kind of see that it's just kind of bouncing around up and down. We might have two in a row that are kind of below, two in a row that are come up above. And we're just looking for that kind of random scatter. A non-random scatter, so we have that arc pattern like so, or there's a couple other ones that we'll take a look at. That is an indication that a non-linear model would be a better fit. We're going to come back to these two vocab terms. I want you to flip over to the next page. So looking at this problem, on the next page, we have infant mortality and years. So you can see that that first column is years. That's going to be our explanatory variable, or our x. And then infant mortality, that is going to be our y. How we can compute our linear regression, which is what they ask us to do in part A, use a calculator to determine the least squares regression line. We'll get into what that is in a little bit. But you go into your TI graphing calculator, press the stat button, and go into calculate. Again, because we are in statistics, AP statistics, we are going to bypass that first option, and we're going to go down to option number 8, a linear regression of A plus B to the x. It's going to ask you for your x and your y to appear in your lists. So I go back to my lists by hitting stat. I'm going to edit them. And in here, I've typed in what I want for my x and my y. So my x here, I've used the years since 1900. You could also type in 1910 as that value as well. I just chose to use the years since 1900, and I'm going to note that in my equation. And then over here, I've also included our y's. So those are our infant mortality rates for each of those years that we have recorded. Then I go back, I hit stats, calc, option number 8. You can either type in the number 8 or slide down like I just did. Go all the way down to calculate, and that gives us our equation. So A is our y-intercept, so that's our predicted infant mortality rate for 0 years, or at the year 1900. And then we have B, which is that slope. So I write that down at the top of my page. See that I have y hat equals, and then we have our y-intercept, 18.5 minus 0.3x. And then down here, I've converted that into like the terms that I would like you to use. So don't use x and y. If you can avoid it, include context, because you're going to need to initialize those variables. So our y is the predicted, that's what that hat indicates, predicted infant mortality rate equals, and we have 18.5, which is our y-intercept, minus 0.3, and our x in context is the years since 1900. So I've included all of those things. And then it says, use the calculator to determine the least squares regression line. For part B, fill in the blank columns in the table above. So we use each of those years, so we plug in 10 into that equation, and that would give us our values for each of those. Let me do that real quick. And you can see that I have 18.5 minus 0.3. So for 10 years after 1900, we have 15.5. For 20 years after, we have 12.5. For 30 years after, we have 9.5. And for 40 years after, we have 6.5. So those are all of the values that we've recorded here in this table. So that was just using our linear model by plugging each of those years after 1900 into the equation. We can then calculate the residual. So the residual is the actual amount, so this 15 for the 1910, minus our predicted amount. So the actual amount minus the predicted would result in a negative number because our prediction is larger. So I'm going to graph that on here, negative 0.5. We can do that again. We can do the actual amount minus the predicted amount, and that gives us an underestimate. We underestimated this time instead of overestimating like we did last time of 1.5. So I go to the year 1920 and then put a dot at 1.5. Then I can come down for the next year to negative 1.5 and go back up to 0.5 for the last year. So we have for each of those years an underestimate or an overestimate. How you can get this residual plot in your calculator is once you've run that linear regression, so I'm going to again press the number 8, run through that, calculate. My calculator gives me all of those slope and y-intercept, but it also calculates the residuals in the background. So what we're going to do, what we're going to graph that is go second y equals. That takes us into our stat plots. We want to go into one of them. We are using the x, or our explanatory variable, as our x list. Our y list we're going to use is the residuals. How you get there is by hitting second stat and scrolling all the way down. Depending on your calculator, you might have a few different things in there, but residual is one of the things that once you've run linear regression, your calculator is going to update that every single time. So that's going to be our y. And then we can just do zoom 9, and there's that exact same graph that we just made. So that's how you can make a residual plot on your calculator, and that satisfies D. Flipping back, sliding down to the bottom part here, we have some more residual plots. So what we're looking for is random scatter. The more random scatter, that is going to produce, or something that indicates, a more better fit for our line. So you can see that in that first graph, we have a bunch of points, no obvious pattern that's I can see in any of those. So that is going to be that a linear model is going to be an excellent fit for that because there's no clear pattern. Sliding down to the one below that, there is a bit of a pattern. As I move from left to right on the x-axis, you'll notice that this fans out, that it gives us that kind of curvature to it. That fan shape is an indication that our line is becoming, or our linear model is becoming less accurate over time, or as x gets larger. So that is a pattern. That means that the linear model is not going to be a good fit. Going up to this other corner over here, we have this U-shaped pattern, so a positive, and then it goes negative, and then it goes back to positive pattern. So there is an obvious pattern in that data, so that means that the linear model is not a good fit. We might want to try something like a quadratic for that particular data set. Down below here, so all of our residuals are approximately 0. You can see the decimal points here. This is a flat, like everything is right on our line. So that means that actually our model is a really good fit. So this is really the only type of pattern that would be acceptable. It's just that everything is dead on. So whatever we did here, it was basically an exactly linear pattern. So going back up here, I can see that there is a little bit of pattern, but that's probably because there's only so few data points. It's not anything that I would consider to be super substantial. So does the plot suggest the linear model is good? I would say there's no obvious pattern. So a linear model is a good fit. There we go. All right. Going back to that other page for a minute, at the bottom there we had 2 more vocabulary terms. So 0.7 and 8 are two more things that you will come across as you look at some of our features of our computations. So one of them is the standard deviation of residuals. Like typically, standard deviation tells us how far something is from like uh, our normal or our average. In this case, our line is going to be that average. So when you're looking at a linear model, there's going to be some amount of variation from what actually is to what we predicted. And that's what that standard deviation stands for. Again, I've provided you with a sentence structure that you can use to help you, like when you see those problems and ask you to define the standard deviation, or what does the standard deviation tell you. And that is when using the least squares regression line, so when we make that model, x equals in context and y equals that thing in context, we will typically be off by about whatever that thing is, whatever s is in the context of the problem. So we're typically off by 10 or 20 or by $50 or whatever that label might happen to be. The last one is another one of those sentences that you're just going to have to kind of memorize and use in the appropriate location. So interpret the coefficient of determination. One of the things that's really important that you include here is, what is the coefficient of determination? That is r squared. You are familiar with seeing r as our correlation coefficient. R squared is our coefficient of determination. So it's one of those another vocab terms. And so the sentence is, the blank percent of variation in y is accounted for by the linear model relating y to x. This is one of those very few times when you are not going to use the word about when you're using a number. So when we're talking about coefficient of determination, we're going to use that exact number because that's referring to the model and how accurate our model is. And that one actually is not rounded. All right, flipping that other page over to the backside, you will see at the top here, we continue with those Ford F-150. So this is on the backside of that infant mortality problem. Referring back to the Ford F-150, at the beginning of the packet, here is a residual plot. So this is in referencing to that first page. Is the linear model appropriate? So we look for, is there random scatter? And as I look at these dots, is the residuals the actual numbers minus the predicted? Remember, that's our residual formula. Residual is A minus P. Actual minus predicted. There's no clear pattern here. It looks kind of random to me. So I would say the residual plot appears randomly scattered. The linear model is a good fit for that data. They provide us with S. They tell us that S equals 5,740.13. So we're going to use that formula from earlier in the packet, from point 7. So that formula structure says, when using the linear least squares regression line with x equals, in this case that's miles driven, and y equals the price of a used Ford, so we're just kind of plugging in the context in the appropriate locations, we will typically be off by about $5,740. So for each one of our estimates, you can see that we are off by some amount. Some of them are super close, but some of them are kind of farther away. On average, these points are about $5,740 off. Some of them are much more, some of them are much less, but they average out to be about $5,740 away. Last thing they ask us to do is to interpret that coefficient of determination. So from the beginning of the packet, they gave us an R value. They gave us that R was negative 0.815. So our coefficient of determination is R squared. So we need to take that R value and square it. So we can do that in our calculator. We can take 0.815 and square it. Because it's a negative times a negative gives us a positive 0.664. So that is going to be 66.4% of variation in, and this is one of those sentences that you're going to use a lot, so you're going to get familiar with it, in the Y, so in the price of a used Ford, is accounted for by the linear model relating Y, the price, to X, our miles driven. So we're using that explanatory variable and the response variable in the appropriate context. That concludes section 2 of these notes. Have a wonderful rest of your day, guys.